Welcome to Daily LeetCode Day 51. Just woke up from a nap that was very, very delightful. Recovery is key. Yesterday we were working on O1 matrix, trying to reach the pretty much optimal time complexity. I think today we're going to be focusing on this problem from a different. We've got to make sure to handle our cards first, and then we can return to O1 matrix and continue generating solutions. But yeah, just woke up, just a little low energy, but the session, I feel a calmness, I feel the silence in my brain. So I think that's a good sign for the session. So I think we should be able to do good. Unfortunately, I'd like to go for the goal time complexity and all these other problems too. We're still on O1 matrix. And that's kind of the major problem with the system. I think in the new system going forward, needs to be blocked and use massive creativity to pass problems when we're stuck. That being said, though, we still have to keep pushing cards along. So it really is, I think, it really is unclear the path to go. But either way, I think only time and data will tell the better solution. Right now, I think these problems at the bottom here aren't very. I think all of them are pretty close to already the goal time complexity, except maybe flood fill. So we should be okay. But want to finish these up, and then in the future, the only problems that we'll have in space repetition are problems that you take into the highest level, which is probably a good thing. So yes, that is what we will do. And yeah, I mean, don't forget to join the hyperbolic coding chamber. Very, very, very huge announcement yesterday. The HCC needs you, right? Because we're growing, and we're already taking up over half of Discord servers, but we need even more people, right? So don't forget to join. A lot of secret tips and tricks and cheat codes in there. So yeah, don't forget to join. And then yeah, let's jump into it. I'm going to set up the timer as per usual. This is going to be a slightly shorter session, just because there's more review to be done later on. So I don't want to make today's session too top heavy. But yeah, there's more to be done, more to battle for. But today's session is going to be a little bit shorter, but I guess it's going to be shorter recorded wise, but there's other prep that I do as well that I think is pretty cool. So there's also some system design stuff that I look into. I mean, part of me just wants to be a better like computer scientist, so I can make more things. So I think there's also a personal interest there, where even for some ideas I have for some applications, just don't have enough skills right now to put them together. So recording those things are less interesting, but it's hard to do 1 hour and 30 minutes of this and then go into maybe 2 or 3 hours of system design. So that being said, let's just jump into it. 30 minutes. Let's do the thing. So we have binary tree right side view. So given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. Now let's map this statement to the problem. So given the root of a binary tree, I want to imagine that we're standing on the right hand side. And when we do that, we get the answer 1, 3, and 4, which is perfectly labeled top to bottom. Now, presumably, the real question is, if 4 was removed here, right, would the answer now be 1, 3, 5? And if 3 and 4, right, were removed, would the answer be 1, 2, 5? And I think just because we've done this problem before, we know that asking questions is important. We know that if we remove these 2 nodes here, the answer is yes to both questions. We'd show 1, 2, 5, as well as 1. If 4 wasn't here, 1, 3, 5. So we know that we want all the nodes on the right-hand side. And for this example, we see that when the left subtree of the node is empty, we should still return the right side view. And for an empty tree or an empty binary tree, we should return an empty array. So we'll just make sure to add that in just really fast so we don't forget. Return an empty array. Now we can look at more things, right? We know that a node range lies between -100 and 100, and that this makes sense, right? So one way to rephrase this problem, right? If we want the right side view, what we really want is the last node in the level order traversal, right? Last node in level order traversal. Since if we have 1 here, the last node in this level would be 1. If we have 3 here, the last node would be 3, and we had 4 here, the last node would be 4. If 4 was missing, the last node in this level would be 5. And so that's really what we want. We want the last node in a level order traversal. And so since there are 2 methods, right, to iterate through a binary tree, you can do a depth first search or a level order traversal. I think we're going to want to go with a level order traversal. And I'm imagining that our time complexity here is actually going to be worst case linear time, where we have to visit the entirety of the binary tree to get the last node in every level, as well as linear space as well, because an iterative level order traversal is typically done with the queue, which can actually have typically done with the queue, which can actually take up to n space, right? If we're going for level order traversal, the most amount of nodes we'll have is actually halfway through the tree, where the tree will be its widest, right? Or at the end of the traversal, we could have you could have an entire level in the queue as well. So worst case would be linear space. So we can take a crack at this level order traversal, right? We're going to want to keep track of the node of the level that we're in. So to do that, we're also going to want a queue with the root node in it. We're also going to want a delimiter, so we can use null, and this delimiter is just going to let us know that when we reach the end of a level, it's going to let us know that hey, we reached the end of a level. So once we put our root node in, we want to start it with a delimiter, because that's going to note that this is the end of our level, right? Then we'll have a loop, right? Loop while queue isn't empty, right? We're going to grab cur, right, off the front of the queue, so we're going to have root, right? Now that we have our root in hand, right, and a level order traversal, right, if cur exists, right, what we're going to do is push its children on, right? So we're going to want to push our children on, right? So we'll say if left, push cur dot left, right? And if right, push cur dot right. So now we're going to have cur dot left and cur dot right, right, onto the queue after this null delimiter, right? Then we're going to go to the next iteration, right? And we're going to need this else, right? Because if cur doesn't exist, then it must be a delimiter. So if we just had a delimiter, right, then we know that our level just ended. And if our level just ended, right, we want to push last element in last level, right? But to do that, right, we're actually going to have to keep track of current level. Say current level is going to need to be an empty array. And the thing is, once we pull elements off of the queue, they actually go directly into current level, right? Because we pull one off, right, in this original part where we start with root and null, we pull one off the queue, right? If we push it into current level, and then on the next iteration we pull null off the queue, right? Current level, right, should be equal to 1, right? Only if, right, when cur exists, we do current level dot push cur. So we should have access, right, to all the elements in the last level, right? And to do that, we can just do, we're also going to want our output, right? Or we can call it RSW for right side view. It'll be an empty array. And we can just do RSW, right, dot push current level, right, sub current level dot length -1, pretty much the last element in the level. So we should be able to do that. And then since we're able to push that last element, current level sub current level -1, there's one more thing we want to, there's a couple of more things we want to do, right? After we push that last element, we're going to want to reset current level at this delimiter, right? We're going to want to reset it back to an empty array, because when we start pulling elements off the queue like 2 and 3 again, we want them to enter current level. And I guess last level is really the best name for this last level, because when you get to this else, it's the last level, right, that we're worried about. So I think a better name for this would actually be last level. Right, now this clearing to the empty array makes more sense, right? We'll clear it to an empty array, right? And I think that does make sense, right? And the next two nodes would be 2 and 3, which are going to end up in last level, right? We're going to push them on, and then, right, once we find that null, right? So now we're noticing, right, in this example, we'll have 2 and 3, right? We just pulled off root, we just pulled off null. We're going to have 2 and 3 in the queue. We have no delimiter right now, but we actually have all the last elements in the end of the last level in the queue right now, or the next level in the queue right now. The next level is 2, 3, right? So to do that, we're actually gonna have to say, right, if the queue dot length does not equal 0, then what we can do is do queue dot push null. And so this should propagate all the way down to the bottom. So when we add 2 and 3, we have a null afterwards, right? We push 2 and 3, right? We pull them off the queue, we'll process them, right? Then we'll find that null, right? We'll add 3, right? But we'll have pushed our children, which would be cur left and cur right. Cur right on both of these, right? And the last element in this level is actually going to be 4. And then at the end, we can return RSW. So I think we can actually try and implement this. So we'll have our queue star, it's going to have root and null in it. Then we're going to have last level, right? Well, const RSW, since we're not going to reassign it at all. And then we'll say, well, we wanted to loop while the queue wasn't empty. So we'll say while queue.length does not equal 0. Right, we're going to want to grab cur like we said, so we'll do const cur is going to be equal to queue.shift, and then we're going to say if cur exists, which we can do just by doing a regular if check. Then we'll take this time here to fill out this else. Now we're going to want to do last level dot push cur, right, to keep track of the last level, and if our left subtree exists, we're going to want to push that child onto the queue, right, to be processed. So we can say queue.push cur.left if cur.left exists, and we'll do the same for the right hand of the node, right? And then we're going to want to push the last element in the last level, right, into RSW. This is our actual answer. That line actually exists here. Let's see if this makes sense. RSW.push last level sub last level dot length -1. Then we have last level equals an empty array. We're going to reset it, and then we're going to have if the queue, right, length does not equal 0. So if the queue still has another level to go, then push null. Otherwise, we don't want this to propagate forever, so we're going to want to end it. And so I think this makes sense. Let's run it really, really quickly for 1, 2, 3, 5, and 4. We push 1 onto the queue with null. Our queue is not empty, so we pull off 1. 1 exists, so we push 1 on to last level. right? Our children exist, so we push both those onto the queue after null. We have 2 and 3 after null here. Then we pull the next element off the queue, it's null. So we're gonna push the last element in the last level array, which is actually 1, which makes sense. Reset last level, right? We have 2 and 3 in the queue right now. We push null after 2 and 3, right? So then we're gonna pull the next one off the queue, which is gonna be 2, right? 2 does exist, so we push 2 onto last level. We push its children, only one of which exists, which is the right child, right? Then we pull the next element off the queue, which is 3, right? We push it onto the last level array. We have 2 and 3. Only the right child exists, so we push that onto the queue. So now the queue has 5. We're on 3, there's null, right? And has 5 and 4. Then we pull the next element off the queue. It's actually going to be null. So we do rsw push last level sub last level.length minus 1, which is actually 3, right? Then we reset last level. There's still 2 elements left, right, to be processed in the queue, which is our next level, right? So we have 5 and 4. Right, so we push a null, we pull 5 off, add it to last level, we pull 4 off, add it to last level, we have no children, right? Eventually we get to null, our last null, right? We push 4 onto RSW, we reset last level, the queue is empty, so there's no point pushing on a null, right? Since there's no next level. And I'll check if our variables make sense, last level makes sense, RSW is used here, our queue is used here, and let's give this a shot. Oh, right, the elements that we're pushing onto last level, right, are the nodes themselves. What we want to do is actually push the values at those nodes. So there we go. So the time complexity here would actually be linear time and linear space to solve this. Given an integer array nums, find the contiguous subarray containing at least one number which has the largest sum and return its sum. The subarray is a contiguous part of an array. So if we're given an integer array nums, we want to find the contiguous subarray containing at least one number which has the largest sum and return its sum. So let's map this problem statement to our example. We have an integer array nums. We want to find a contiguous subarray containing at least one number, right, which has the largest sum. So we can't change this since we have to use the contiguous subarray. The largest sum is actually be 6, or returning a number. We have 4, -1, 2, and 1, which is the best sum we can actually do, right? It always has at least one number, so the best sum we can do here is 1, and so on. The best sum is all these numbers added up together, right? And then we have 1 is less than, so we know that we'll always have at least one number in nums.length, and the range of the numbers is -10 to the 4, 10 to the 4. So the answer is really much predicated on the order, so you can't sort or anything like that. So you kind of have to do this as is. So I'm thinking the best way to go about this problem is probably to do with the sliding window pattern, where we can basically visualize our problem as a sliding window that slides over this array of elements, but only we'll be able to choose when this window shrinks or expands depending on the implementation of the sliding window pattern. I think in this one we're going to want to always be expanding and then decide when to restart our window. So if we just looked at this example right here and tried to come up with a process-driven approach, right, we start with -2, right? We add 1 to our window, our new sum is -1. Add -3, our new sum is -4. Add 4, our new sum is 0, right? So we're continuously going here, but at this point we know that the answer is 4, -1, 2, and 1. So we need to find a way to restart that makes sense. Because going this far, we're already not able to build the answer that we're looking for. So by the time we get to 4, we're actually just now reaching 0. But our goal sum is supposed to be 6, right? So we know that the sum that we have is inadequate to some degree. And I think we can tell that the sum is inadequate because we're looking for the largest sum, right? And if we're looking for the largest sum, then we're going to want to make certain that we're going to want to know, right, when keeping the number we have, when do we restart the window and when do we keep the window that we already have? And I think we restart, right? I think we can see, right, with -2 and 1, right? There's no point having these two numbers together because we're better off just having 1 to start. So I think what we're actually going to want to do is when we have 1, when a number itself, so we'll say, if a number itself, we'll just call this num sub I, and assume we're iterating through it. If num sub I is greater than current sum plus num sub I, so like we can see here, right, -2 is our current sum. If 1 is greater than -2 plus 1, then we want to restart with 1, right? Because that's kind of our goal here. Otherwise, keeping this -2 doesn't really help us. So we'll take 1, right? Then we go to -3, right? Is -3 greater than -3 plus 1? Let's see. No, right? Wait, let's see. Is -3 greater than -3 plus 1? No, right? So since -2 is not greater than is -3, we have -3 here greater than -2. No, -2 is greater, right? So we'd keep going, and then we get to 4, right? We're going to say, hey, is 4 by itself greater than 1 plus -3 plus 4? Yeah, right, because that answer would be 2. So 4 is greater than 2, so it's better just to restart here at 4. Right, and I think that ends up working to our favor because the greatest sum we can ever create is this sum right here, right? And we'll be constantly taking the math.max as we're moving forward, so I think this actually could work. So let's try and scaffold it. We'll iterate through nums, right? We'll say if num sub I, right, is greater than current sum plus num sub I, right, then we'll say current sum equals num sub I, right? Else, right, if it's not, we'll just add the number and hope that eventually our sum will be the greatest it can possibly be. I think another reason we're going to want to make sure to check if the current sum plus nums, right, is less than num sub I, right, is because if at the last element in the array we have 4 trillion, right, and let's just say the sum of this entire array, even if with all of its negatives, right, equals just 1, right, the answer would still be the entire array because 4 trillion plus 1 is still bigger than 4 trillion. So we want to take sort of a greedy approach. So we'll say else, we'll just do it as normal, current sum, right, we'll just continue to add numbers sub I. Right, on each iteration, we'll take, right, we'll keep a value, right, which we're going to call max, which we can set equal to num sub 0, right, since we know that there's always going to be at least one element. We'll set max equal to the math.max of max and current sum, right, and then we can return max. And so let's see if this makes sense. We're iterating through, right? We're going to start with, our max is going to start as -2, right? Is -2, and we can start, since we're iterating, right, through nums, we can start at 1, right? And we'll say, hey, is 1, right, greater than 1 plus -2? No. Well, is 1 greater than -2 plus 1? It is, right? Because -2 plus 1 would give us -1. 1 is greater than -1. So you want to add we want to just set our current sum equal to 1. So our new max, right, after the first iteration, which starts at 1, is actually 1, which is perfect. And then after this point, after we get to -3, is -3 greater than -3 plus 1? It is not. So we'll take the current sum, we'll add -3 to our current sum, right? And then we're going to say, hey, is 4 greater than 4, right, plus -3 and 1? Yes, right? Because our previous answer here would be 2. 4 is greater than 2, so let's just restart with 2. And then I think we should be good to keep adding, because our restarting with our current sum is never bigger by itself. So -1, 2, and 1 is never larger, right? Plus that number plus our current sum is never larger than the current number by itself. So basically, a better way to say it is the number 2, right, plus our entire window so far, which is 4, -1, right, and 2. 2 is not greater than this entire window together, right, because 2 is not greater than 5. Right, so we just add it. And then we have this greedy approach, which keeps adding numbers, but eventually our best sum so far is still 4, -2, and 1. Then we had -5. It doesn't really matter, right? We had 4, and we end up actually creating a new sum of 5, but it's fine because the maximum sum we ever got was 6. So I think this does make sense. Let's try let max equals num sub 0, and we're going to iterate through num starting at 1. Do I is less than nums dot length I plus plus. We'll just set up this else clause just to make sense, right? And we'll say nums, right? We need a current sum variable. So we'll let current sum equal to num sub 0 as well, since we're going to start at the second index. So we'll say current sum is equal to num sub I, right? If that statement is true. And then we'll say current sum plus equal num sub I in the case where it isn't. And then we'll constantly be taking the maximum of that in current sum, and then return max. This makes sense. I think the time complexity of this would be linear time, since we're just visiting every number in nums, right? We're doing a small operation, which is either a max on every operation or an assignment. So I'd say our number of operations would be linked directly to the number of elements in nums. So given the root of a binary tree, we want to invert the tree and return its root. So we have this first example. What does an inversion look like? We have this binary tree of 4, 2, 7, 1, 3, 6, 9. And we can see that on this right-hand side, its children are flipped. We have 2 and 7 and 2, right? We had 7's children, right? Which now are also flipped. We had 6 and 9, now we have 9 and 6. First we had 1 and 3, now we have 3 and 1, right? And even in a smaller subtree, we have 1 and 3, now we have 2, 3 and 1, right? And when the input is empty, we actually just want to return an empty node. So the number of nodes in the range is actually can be 0. And so if that's the case, right, we'll just say if the root doesn't exist, well then we'll return null, right? But as far as reversing the nodes, what we could do is just a depth first search. Starting at the first node, right, we'll swap the 2 children and then visit the children and swap their 2 children and do this continuously. The potential time complexity there would be linear time with linear space as well. So maybe we could have a secondary function called DFS, which would take a node to start like the root node, Would it need anything else? I don't think so. We'll keep going with it and see if we'll need to change it. And then we could have this function right here, which would take a node, which could be a tree node or null. It doesn't return anything. And then the goal here, right, would be to swap the children, right? Only if it exists, right? So we want to say if node, right? If node, then that means the node exists, right? We want to swap the children. So to swap the children, we'll create a temporary value, right? So we'll do node.left. So we'll say the node.left subtree, right? Then we'll say node.left equals node.right. And then we'll say node.right is going to be equal to node.left to swap them, right? And then we can do DFS, right, of node.left to swap the left node's subtrees as well as the right node's subtrees. And a better function name could be swap or invert. And maybe we could fuse this DFS and invert tree function. But if we visit 4, right, as a test run in our minds, we'll visit 4, it exists, right? We save our temporary value of the left node, then we set the left node to the right node, then we set the right node to the left node's value, so we swap it, then we visit the children. We actually end up visiting 7 first, so we go to 7, 7 does exist, we swap its children, right? Then we call DFS for 9 and 6. 9 exists, right, but it has no children, right? We DFS on its child nodes, which are null. It does nothing, it ends the recursive loop. Ends the recursive loop. Ends the recursive loop, and then we do the same for 6, right? But we've already swapped them. Then we're going to do the same. We're going to come back up to 4 and do the same thing for 2, and then swap its children. So let's try that. Interesting. So we're actually losing values. So we have temp is equal to node.left. Yeah, so we're actually losing values somehow. Oh my God, we didn't even use our temporary value, which we saved. So the swap factor So there we go. This would run in linear time with linear space as well, since we have to visit the entirety of the tree. There's not much time left, but we'll just wrap up these last 2 problems. Given an array of integers, nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If target exists, then return its index. Otherwise, return -1. You must write an algorithm with O of log n runtime complexity. So this problem, I usually try and explain every problem, but we know that this problem is just asking us to implement a binary search, and we can do that. We can say let left equals 0, right? Let right is always going to be equal to the last possible index in the array, right? And while left is less than or equal to right, in the sense where it's possible that an element, right, our array could have only one element, right? All the integers and nums are unique. Nums is sorted in ascending order, which are all the requirements for a binary search, right? We're going to want to calculate our pivot, which is going to be left plus the math.floor of right minus left over 2, right? And then we're going to say if nums sub pivot equals target, right? Then we're going to return pivot, because we found, what do they want us to return, right? Then return its index, right? So you want to return pivot, which is our actual number that we found. Otherwise, right, if num sub pivot, since our array is sorted, if the pivot is actually greater than our target, then we know every element after the pivot is also too great for our target, right? And if that's the case, we can cut our search space in half by doing right is equal to pivot minus 1, and we're subtracting 1 from pivot because we actually just processed this particular pivot, right? If we set it equal to pivot, we would end up processing pivot twice. So we set pivot minus 1 because we don't want to revisit pivot. And so we'll do something very similar for when our generated index, right, and the value at that index is less than the target. We're actually going to want to do left is equal to pivot plus 1, right? So if we generate a value, an index, right, we go to that index, and this element is smaller than our target, because our array is sorted, every element before this element as well is also too small, so we can skip it, right? And then at the end, we're going to want to return the right well, if we found through here, right, then it's possible that we exit through here, right? But it's also possible that our last index is, actually no, I'm pretty certain that you can just return -1. It depends on why you need to binary search, and you can be concerned about where you end. But in this case, we can return -1 because if the value doesn't equal target, right, the pivot we generated doesn't ever equal target, then we never exit through the while loop. If we never exit through the while loop, then we want to return -1. This would run in log of n time. So then we have an image is represented by an m by n integer grid image, where image sub I sub j represents the pixel value of the image. We're also given 3 integers, SR, SC, and color. You should perform a flood fill on the image starting from the pixel image SR sub SC. To perform a flood fill, consider the starting pixel plus any pixels connected forward directionally.